Great. Okay. So let me share the screen. There we go. See if I can hide this. Very good. Okay, let's cover a few things first about the experiments that you just finished and some of the lecture material before we get into op amps. Okay, so to avoid mistakes, does a protoboard circuit look like the circuit diagram? Here's a circuit diagram on the left, and you can see on the right the circuit board. So here's a transistor. Below that is a resistor, transistor, resistor. Here's the input resistor on the left of the transistor. That's right here, R3. And then there's this biasing voltage that's added to whatever the input is. So there are two resistors here that look like, that are vertical, like they are here. And then the capacitor on the left here for the to block any DC voltage coming into the circuit. If we just want to amplify an AC signal, we want to get rid of the DC because that would give us a bias. So we use a blocking capacitor that blocks DC. Okay, and you know, fairly simple circuit diagram here, circuit wiring here. That'll become very important when you get to digital circuits because you'll have lots and lots of wires to hook up in chips. Okay, I won't say a whole lot about the semiconductors that we did last week, other than I hope you all know about doping, N-type and P-type, how a junction diode works. How does a depletion? What is a depletion region? And how does a diode work? I mean, this is not only important for diodes, but it's also used in FETs. So there are billions of these things in your phone. Okay. Any questions on this so far? Can somebody say something? Make sure I can hear you.
We can hear you.
Okay.
Yeah.
Great. I can hear you. Fine. Okay, we're all set. Okay. Review of transistors. Just basically, we look at a transistor as a variable resistor, and we use it in a voltage divider. And I'll show you that later in op amps. Okay, FET, a field effect transistor. It relies on this depletion region of a PN junction. I mean, here's a picture over here, and it operates simply to close the cross-sectional area between the source and the drain here. So it uses the PN junction PN junction effect, basically. But all you're doing is changing the cross-sectional area. Very simple, very physical. Okay, you go from FET to MOSFET. What does MOSFET do? Metal oxide. Basically, MOSFET just means that you have an oxide layer on the gate. So look at this diagram on the left here. Notice that the gate, AA here goes into the two gates of the FETs, the MOSFETs. But you can see that there's a separation here. There's a gap between the gate and the source and the drain. So there's not electrically isolated, but it's isolated in the sense of having an insulator there. I mean, you can still feel an electric field through it, but you don't get any DC current through it. So that's what the oxide does. That's the second thing. The third thing is CMOS, complementary MOS. Okay, that's very important. that one FET is always off. Okay, complementary means if you have an FET that you put a voltage on, it turns on, then you have another FET when you have a voltage on it, it turns off. So whatever input you have here on A, one of these things is always off. So it says you don't get any current going from here, from the, say, the source to the drain. You don't get any current going from here to here through this thing because one of these things is always off. Okay. So no current flows in it. So that is really, otherwise if they didn't have CMOS in your phone, you would be charging it probably every 15 minutes or less. Okay. Any questions on this? 3 big points here: FET, an oxide FET, and a CMOS. Okay. Okay, let's move along. Operational amplifiers this week. We're gonna look at some basics and how to use them in some circuits. Why op amps? Well, basically, electrical engineers have put a lot of work into putting various components, various transistors together, and taking all the work and making it much easier for you to configure a circuit using an op amp than a transistor. Okay, engineers have done all the work. That means less work for you. I will go over the golden rules. How do you design the gains? Get some very simple formulas for that. What can you do with op amps? Well, you can make different kind of amplifiers, and we'll go over that. And then op amps can do math. They can sum, take the difference, differentiate, integrate, and you'll actually do these in your experiment this week. You'll make a differentiator and an integrator. Okay. In audio amplifiers, you can buy high power op amps that have basically high power transistors in them, so you can get you can get something that has 100 watts in it, and it's simple to design. This is a picture of all the stuff in your iPhone, and here's 1, 2, 3, 4 power amplifiers, and they're some kind of op amps here. I mean, if you're going to have a speaker, you need to put power into the speaker or the earbuds. If you have earbuds, you have to put out a signal at 1.8 gigahertz to transmit information. So you have all these amplifiers in your iPhone that are probably based on op amps. Of course, whenever you have a speaker, radio, television, you're going to need some sort of higher power in an amplifier. Acoustic amplifiers. Okay, let's go through the linear amplifier. In a lot of cases, for like an audio amplifier, you want to take some signal from, say, a microphone, and you want to amplify the power or the voltage, and you want it to give a representation, exact representation of what was going into the microphone, only louder. Okay, so we'll talk about a device that has 4 terminals. It has several inputs, at least 2 inputs and 2 outputs. And as before, we're going to define gain as just what goes out relative to what goes in. You can amplify voltage, current, or power. So voltage gain is just we call it G sub V. We'll just call it G sub V. And it's just the voltage out divided by voltage in if it's a voltage amplifier. You can have gains that are much greater than 1. You can have them 1,000,000. You can have a gain of 1,000,000. You can have a gain of 1, which we call unity gain. Sometimes you just want to amplify the current and not the voltage, and that's used a lot in digital circuits. You can have an attenuator. If the gain is between 0 and 1, what you get out is less than what you put in the voltage, and that's an attenuator. You can also have inverting, and op amps are great for inverting signals. Here's if it's less than 0, if the gain is less than 0, like -3, here's an example of the blue curve is a sine wave V sub in, and the red curve is V out, and it's 3 times the size, and it's a negative of it. So like when V in is negative here below 0, then the output is positive. V out is positive. So it's out of phase basically, but it's a negative of it. Okay. Often when we talk about gain, because you have such large values, 1,000,000 gain, usually anything that goes as the power of something, we like to use decibel units. I mean, decibel units is also used in sound. But here, voltage gain, if we just talk about voltage, then the gain would be 10 to the dB over 20, or the dB of something is the log base 10 of the gain times 20. It's just defined that way. So when you talk about a voltage gain of 1, that's 0 dB. If you talk about a voltage gain of 1,000, that's 60 dB. So for every order of magnitude, so every power of 10, you go up 20 in the dB value. Okay, looks a little bit like sound. The threshold of sound is about 0 dB, and threshold of pain is about 100 dB. Okay, but these are just voltages. Okay, we know that power is equal to voltage squared over resistance, and that's if resistance is a constant, of course. So the power gain is just a factor of 2, exponent of 2 different than voltage gain. Okay, so it's 10 times the log of the power gain rather than 20. So in power gain, every order of magnitude change here, every step up of a factor of 10 is an increase in 10 dB. Okay. Okay, we're actually going to use that, and you're going to measure gains in dB. Any questions here so far? Looks like we're up to about 51 students out of about 60.
Hi, I have a quick question. This is just for clarification.
Sure.
So going back one slide, so when the voltage gain is greater than 1, that's just implying that the voltage is increasing, it's being increased by the gain?
When the gain is greater than 1 or less than?
Greater than 1.
Yeah, greater than 1. Greater than 1 means V out is going to be larger than V in.
Sure. Yeah. Okay, thank you.
Right. That's all. Great.
How does this decibel scale work for negative gain? Because you can't do the log of a negative number.
Negative. Yeah. Okay. I haven't had to deal with that. I guess you just call it negative. Negative. Yeah. if you're talking about a negative dB value, I guess you can't use that. Yeah. Yeah. Great. I mean, you can see here a gain that's very small, less than a voltage gain less than 1 has a negative dB value, but it doesn't mean it's inverting. It's not inverting. Yeah, good question. Anything else? Okay. Okay. I always like to throw in a little bit of history. I mean, this history goes way before me. I mean, you might think I'm pretty old, but these things go way before me. Negative feedback is very important. Negative feedback is required for self-regulation or to control the gain. Okay, and it was in electronics. It was kind of discovered in 1927. Negative feedback. Harold Black developed it. He was right. He worked at Bell Laboratories, which I guess was in Manhattan for a while. Then it moved to New Jersey. But it was a premier research laboratory in the world for many years, up until Bell Telephone was broken up into smaller pieces. So that, but it was for many years. They did a lot of electronics. I mean, it's named after Alexander Graham Bell, right? For the Bell telephone, and it has, they've done a lot of work in electronics. So anyway, he was on this ferry, and he came up with this idea, and he didn't have anything to write on. So he had this newspaper. You can see Saturday, New York Times, Saturday, August 6, 1927, and he started scribbling down these notes on how you take some of the output. Here's a voltage divider here, and he's taking some of it and putting it back up into here. So the way patents used to work in those days, up until just 15, 20 years ago, that if you wrote down something somewhere and either you notarized it or you had somebody look at it, if you disclose it to somebody and they witness it, then, I mean, it's witnessed here by somebody else, and you could use that and take that to court and say, I was the first one to think of this and I should get the patent for it. So he actually used this piece of paper probably in court to, for Bell Labs to get a patent for negative feedback. Well, it's not that straightforward. If you work for a company, the company owns everything you do, basically. So, I mean, the company may make hundreds of millions of dollars on something, and then they'll make you a vice president. I guess that's what you get out of it. Anyway, there's an interesting article here that, if you want to read about, read the story about how he came up with this. Yeah. And then a few years later, Harold Black and a couple other people used that in an amplifier. I mean, before that, it was just an idea, and then they actually made an amplifier. And 11 years later, they actually made something with vacuum tubes. Was used in radar in World War II. Look, they achieved a gain of 90 dB. That's a lot, right? I don't know whether that's voltage or power. Probably voltage. So it's up. What is 90 dB? Let's go back. So if it's a voltage gain, it's 90 dB. 90 dB would be 30,000, I guess. So that's probably what they're referring to, about a 30,000 gain in voltage. And then they realized that, wow, you could have a non-inverting input. And not only, see, negative feedback means you want to put something negative back into it, but sometimes you want a non-inverting input, and even two inputs. And we'll get to that. But it was a footnote in a paper. There's a footnote that a student came up with the idea of having a 2-input op-amp, and that's what we have nowadays. Okay, so this led to the first op-amp to have inverting and non-inverting inputs for an amplifier. Okay, a little more about the history. Well, not so much a history, but the first op-amp was invented in this first semiconductor op-amp was invented in 1966 at Fairchild Semiconductors, and it was called the first useful one that was used widely is called a 741 General Purpose Operational Amplifier. And came out in 1968. And let me go back one. So you're going to be using one of these. They still make them. They cost, I don't know, 25 cents, depending on how many you want to buy. It's in a little package, a little square package that's only ½ an inch long, little black package there. It has 8 pins for one of these, for one amplifier. And it's called 8-pin DIP. DIP means dual inline pin. So it means there's pins on both sides and they're in a line so that you can plug them right into a circuit board, a proto board like we have. Okay, and you're going to be using this one this week. Okay, so here's the circuit. Okay, it contains 20 transistors, a bunch of resistors, 1 capacitor. So it has 2 inputs. It has an input here, where's the other input? No offset. Where'd it go? Yeah, okay. So here's one input here. Here's the other input here. And then there's an output. One thing about an op-amp is often you want to swing a voltage positive and negative, especially if you have something that's like audio. You know, you don't need to go from 0 to some 10 volts. You can go plus or minus 5 volts, say. So here's the output, and the output can go from the plus supply to the negative supply. So in almost all op-amps, you have 2 power supplies, a positive and a negative power supply. And here, this would be the positive side here, and this would be the negative side here, and this is the output. So these are voltage dividers, right? You have some resistors and transistors, and they're going to act like voltage dividers. So this output can swing between a voltage that's as high as plus V, and it can swing as low as a voltage of minus V. So it can swing in either direction, but it's just a voltage divider. Resistors and transistors. The transistors are turning on and off some way where you can change the output here. I mean, essentially this pair here of a transistor and a resistor, and this transistor and a resistor up here are another pair. So then it's this pair versus that pair where you're looking at the resistance changes. But again, an amplifier, you don't get something for nothing, that you're always just taking what voltage you give it and it's going up to that value. Okay, so an amplifier, it could be just called a voltage separator, that you're getting less than what the power supply is. Okay. That's not true with a transformer, right? We went over transformers that you can get much higher voltage out than you put in. Aha, but you can't get more power out. Okay, voltage divider. A lot of YouTubes on that. Any questions so far on that? I think the main point is the engineers have done a lot to put this thing together and to make it easy for you to design. That's the point. Yeah, somebody had a question?
I was just curious of like the physical scale of the op amp, if that whole integrated circuit is contained within it.
Yeah. Well, okay, and that little chip is about 1/2 inch by 3/8 of an inch in size. So it's, you know, it's roughly the size of a dime, and it has 9 transistors in it. And that was, I mean, that design goes way, way back, 1968. Now they can pack things much, much closer, but you can imagine how small things need to be. If you take, I don't know, the microprocessor in your phone or computer is, I mean, suppose it's roughly an inch square. And if you get 1 billion transistors in that, they have to be very, very, very small. So the way they make these things with lithography, they make wires that are, I think they're pretty close to like, the wires are like 30 to 50 atoms wide. Okay, so they can make very, very small devices. So your question was about the 741, right?
Yeah.
Yeah. And about the size of it?
I was just curious. I
Yeah.
didn't mean to go off on a tangent.
Yeah. No. Okay. Op amp, or I don't know. Some people put in the hyphen, some don't. Okay, so here's this triangle represents an op amp. It has 2 inputs and a ground, relative to ground, and one single output in general. And one of these is called an inverting input, the negative one, and the plus one is called a non-inverting input. Okay, non-inverting, inverting. Okay, so what it means is, like, you know, if you have a non-inverting input, that is, if you put a voltage here on the plus and it increases, voltage increases, then the output is going to increase. Okay. If you put a voltage change on the inverting input, the negative one here, if the voltage goes up here, then the output will go down. And that's the way it works. So here's for the, but often you want to know what's the difference between the voltage between the 2 inputs. Okay, so the voltage out is equal to some gain times the difference in the 2 voltages that are put on these things. So the gain is proportional to the difference in the 2 voltages here. If this voltage is greater than this voltage, if the plus is greater than the minus, you get an output that's positive. And if the voltage on the negative one, say this is 5 volts up here, and on the plus is 4 volts, then you're going to get a negative voltage out here. Remember that in these op amps, you're going to put in 2 power supplies, basically, like plus 15 volts and minus 15 volts. So in that case, you could get out a voltage that's close to positive 15 or an output that's close to negative 15 volts. Okay. Okay, so here's an example of gain of 10. If you put 1 volt in the negative here and 0 volts here, and then you're going to get an output of minus 10 volts. Whereas if you switch the inputs around, you put 1 volt here on the positive one and 0 here, you're going to get minus 10 volts out. Okay, if you have a gain of 10. Questions?
Yes, I have a question.
Okay.
Do the initial voltage direction matter? Because the absolute values on V plus and V minus, which say they don't, but normally in circuitry they do.
Yeah, we'll get into all that next. You know, putting different voltages into them. Yeah. Okay, and I mean, if you just kind of remember this, that if one voltage is higher than the other, then you're going to get, if whatever on the plus is higher than the minus, you're going to get a plus voltage out. If whatever on the negative is higher than what's on the positive, then you're going to get a negative out.
What's the significance of the ground on the diagram?
What?
What's the significance of the ground on the
Okay.
diagram?
Okay. Yeah. Okay, so all the voltages we're going to measure are relative to ground. Like in the 2 power supplies that you put in plus and minus are going to be relative to ground. And then the inputs are going to be relative to ground. So basically, if you put a battery between, say, the plus and the ground, that's plus voltage. Or you could put a battery between the minus and the ground. But all of the voltages in the circuit are related to having a voltage is a potential difference. So it's the difference from ground. And we're just defining ground as 0 volts.
Okay, thank you.
Yeah. Any other questions? Okay, I mentioned about the power supplies for the op amps. So most op amps need these dual supplies. So here's part of the answer to your question about ground. So here's a plus voltage here relative to ground, and then here's a negative voltage here relative to ground. And in the circuit here, I mean, here's your 2 inputs here, pins 2 and pins 3. Pin 6 is the output. And then you want to supply voltage to it on 2 pins. So you put some positive voltage on pin 7 and some negative voltage on pin 4. And each one of these input voltages of your power supply is relative to ground, kind of like what's shown up here. Okay, there are op amps that work with just one power supply. I mean, because you think about it, if you're building a circuit you want to carry around, you have a 9-volt battery in it. You know, you don't want to have 2 9-volt batteries. So some chips you can use with just one voltage source. Some are made that way. Okay, so the power supply, you have to power it, but then you throw it away. You don't put that in your circuit diagram. You assume that that's there because they all have that. It just makes things more complicated if you have to say each time that you're putting in some voltage sources. Okay, here's something that, you know, as I mentioned a number of times, that an amplifier is only as good as whatever voltage you put into it. You cannot get out more voltage than the power supply. I mean, you can have an op-amp circuit or an op-amp that has 10,000 gain. But if you put 1 volt in, say on the negative, and 0 volts on the plus, the difference in voltage here is 1 volt, right? 1 volt times 10 to the 5th would be what? 100,000 volts, right? Well, you certainly can't get that much voltage out of it. You get minus 15 volts if that's what you put in for the power supply. And if you put in on the plus, you put in 1 volt and 0 on the negative, then you're going to get out the supply voltage plus, like plus 15 volts. Okay, you cannot get out more output voltage than the power supply. Sorry about that. Any questions? Okay, let's move on. The ideal inverting amplifier. Okay, here's the integrated circuit here, this triangle, and we're going to put 2 resistors on it. We're going to ground the positive input, and we're going to put 2 resistors connected to the minus. Okay, and here's the power supply, but this is the only time I'm going to show it here. Okay, this resistor is called the feedback resistor because you're taking some of the voltage from the output and putting it back into the input. So there's your negative feedback there, going back here. What happens if this was turned around and you tried to put some of the output onto the positive one? You get positive feedback. So that's like, everybody knows what probably what's seen when you have a microphone in front of a speaker, right? A little bit of sound coming out of the speaker goes into the microphone. Then the amplifier amplifies that, puts out a louder sound. That louder sound goes into the microphone. That's amplified again, and it goes round and round until the whole thing saturates, and then the amplifier puts out a squealing noise, very high frequency, out to the speaker. So that's what happens when you have positive feedback. So, but we're having negative feedback. We're putting it back onto the negative side. Okay, so how do you figure out this circuit? Golden rules, very simple golden rules. These are assumptions. They're not strict. The op-amp input voltages are equal, okay? So it's called the virtual ground approximation because if you're grounding this positive one here, then these 2 inputs, not this input, this is a circuit input. These are the op-amp inputs, that the op-amp inputs are going to be the same voltage, okay? Same voltage. And the beauty about the circuitry in here is that this circuit, in a way, is so smart that it's going to change the output voltage, putting back a voltage into the negative one until these 2 voltages are equal. Okay? It changes the output voltage until these 2 things are equal. That's what the magic is. That's what the magic of the 9 transistors do. Okay, equal input voltages of the op-amp, not the circuit, but the op-amp. Virtual ground approximation in this scheme here. Number two, you don't want to have any current flowing into here. So the input impedance of op amps is usually very high, close to a megohm. So almost no current flows into here. So whatever current flows through R would also flow through RF. Called infinite impedance approximation. Your 741 has like megohm input impedance, but a FET op amp would have gigaohm input impedance. Okay. Okay, and the magic is you're designed so that the output adjusts automatically to make the two op amp input voltages equal. Wow. Great for us when you're trying to design a circuit. Okay, so when we have a circuit like this, we draw an equivalent circuit, and that's what this is. Two resistors, V in, V out, V in, V out. And at this point here, it's virtually ground. It's virtually V equals 0. Well, I mean, it is grounded here, right? So that is V equals 0 on the plus. But this voltage is going to be the same as that one. So that means they're both going to be at V equals 0. This point's going to be at V equals 0. Okay, no current flows into the input. That means whatever current flows through R flows through RF. Okay, nothing flows into the ground or into the op amp. Okay, just assume current going counterclockwise. Okay, note that current, so the current is towards V equals 0 for the resistor R. So if this is a certain voltage, then the positive current would flow this way. And it's going the opposite direction for V out. The current's going out. So if this is V equals 0, if it's positive current, this has to be a higher voltage. Okay, so that V in and V out are going to have opposite signs. So that means that G is negative. G is negative. Okay, assume the same current flows through either one. And you have the same current flowing through either one, and you get the ratio of V out over V in, and it's just minus RF over R. What could be simpler, huh? What could be a simpler formula than just a ratio of two resistances to give you the gain, huh? Very simple, very simple. Let's see. I think I'll just have you take a look at this. Well, let's see. Do we have time? Yeah, let's just try it.
In this video, we're going to take a quick look at some of the basics of op amps, and not so much
How's
to
that?
talk about the design of op amp circuits.
We can see it now.
Or an in-depth analysis.
Yes.
But hopefully, just to give you an easy way,
Yes, we can.
to
Okay.
understand the operation of most op amp circuits. And sometimes that's really all you need is say, what is this circuit doing? You know, hopefully with these little hints I'll give you here, you can understand what the circuit is doing and make some sense out of it. So in order to do that, we'll first consider just a couple of ideal properties of an op amp. One is that the inputs to the op amp, the non-inverting and the inverting inputs, basically draw no current. The reality is they draw a little, but for the ideal purposes, let's consider they draw no current. We also consider that the voltage gain is huge, okay? And yet another way to think about that is that a tiny input voltage difference, a very small voltage difference between these two inputs will cause a huge output voltage swing, okay? These two properties will really help us to understand how almost all op amp circuits work. by taking one more factor into account, and that is that nearly all op-amp circuits use negative feedback in some form. Here's a really simple form, just a resistor negative feedback here. And let's look at why that's important. And this is really the key. Negative feedback keeps the input voltage approximately equal to 0. Okay, how does that work? So if you think about that, let's say we had a small positive voltage appear here at Vn. Okay, that small positive voltage would bring this input greater than ground. As soon as that goes greater than ground, this output starts going down. As it goes down, right, some current is going to be pulled down through this resistor, okay, and will be pulling down on this node. So this voltage is bringing it up, the negative feedback is bringing it back down. It's going to keep bringing it down until that voltage difference goes to 0. Okay. And another reason for that is obviously the current that is going in this resistor is not going to go into the input. It has to go through that resistor. Okay. So another way to think about this, maybe in more layman's terms, is the output will do whatever it can to make the input voltage equal. Okay. So that way, if you know what one input voltage is, you know what the other one is. Let's go apply this in a.
Okay. Stop sharing that. Share that. Good. Okay. Okay, questions on this? I assume you can hear me now.
Yes.
Yep, we can hear you.
Great. Okay. Okay, this is just for one of the homework problems, that there's something from the golden rules. You get the nominal gain, okay. But then there's a real gain. What does a circuit actually provide? Okay, because the golden rules are, they're approximations. Okay. So you have the nominal gain, the real gain, and then the open loop gain is a property of the op-amp itself. So these things are all connected. So here's a nominal gain, just a ratio of resistances. The real gain, it has this other factor in, that's the open loop gain. And the open loop gain can be very large, like 10 to the 5th. So here's a problem. If you have these two resistors, say this one is 10 k ohms, this is 1 meg ohm, so you have a gain of 100, minus 100 actually. And then what happens if you have open loop gains? You have different op amps that have open loop gains of 10,000, a million. Okay, so then basically you just have to plug into this formula. You have a nominal gain of minus 100, and then for a very low gain, open loop gain here, the gain that you're actually going to get out of it is 10, whereas what you calculated, what you should get is 111. So it's only 1/10. The gain is only 1/10 of what you expected because A is low. Okay, when A is high, then you're going to get a million gain out of it, even though you only have a very small difference in what you calculated. Okay, so the percent error between the two gains, the real and the nominal gain, is just G over G0 minus 1. Okay, but G has this A factor in it. Anyway, this is just for the homework problems. Okay, this lecture isn't as long as some of the others. I'll skip a few things just to point out a few things that are important. We talked about the open loop gain already. That's just a function of the device itself. Then there's something, the input offset voltage, and you're going to see this in a later experiment, that they can't match the transistors perfectly inside of one of these circuits. Okay, so it looks like there's always a little bit of voltage here, even when you try to put no voltage difference here. So you're always going to get some small output coming out of it, even when you don't put anything into it. And that's just because they're not, the 741 is not perfect. You can spend more money and get ones that have a different input offset voltage. So basically, it's like 2 millivolts that's put into here. That's just a function of the circuit. That, it can be less than 2 millivolts, and it often is. But there's always some little amount of voltage that it looks like there's a voltage here even when you don't put anything into it. So then you get some voltage out when you don't put anything into it. Okay, just wanted to point that out. Okay, here's something you're going to do on your experiment this week. You're going to measure the frequency response. Okay, and the frequency response is given to you in a number called the gain bandwidth product. It says that the gain and the maximum frequency that you can use to get that gain is a constant. And in general, it's like 1,000,000, and the units are hertz because gain is dimensionless and frequency is hertz. So 741 has like 1,000,000 hertz gain bandwidth product. In other words, what that means is if the gain is large, you cannot amplify high frequencies. And if you want to amplify high frequencies, you have to keep the gain low. There's a trade-off. So here's what a 741 gain bandwidth product looks like. Okay. So this is an equation. Here's gain and frequency, and that's equal to a constant. And here's a log scale, and then here's the gain bandwidth product here. So if you're going to design an optical amplifier and say you want a gain of 100, then it'll operate up to 10 kilohertz. Okay, so you'll get a gain of 100 for low frequencies up until about 10 kilohertz, which is close to our maximum response for hearing. Okay, so that'll be good. So you could use this if you wanted to amplify an audio signal with the 741. If you needed to amplify it 10 to the fourth, a gain of 10,000, then you wouldn't be able to amplify anything higher frequency than 100 hertz. So 100 to 10,000 is roughly your audio frequency here. So you couldn't use a 741 for high frequencies. Okay, I'm sorry, high gains. Okay, so If you're amplifying a very low frequency signal, you could have a high gain. So what you're going to do in your experiment is you're going to measure gain as a function of frequency and see where this drops off. Okay. Okay, questions? And what they're talking about bandwidth is, bandwidth just means a maximum frequency. They're assuming that the width means from, 1 hertz or almost 0 hertz up to some frequency. So it's called a width, even though it's a maximum. Bandwidth, gain bandwidth product.
I have a quick question.
Sure.
What exactly is that frequency referring to?
This is just something that's a property of the particular op amp. And that's just a given number. Like if you look up for 741, they'll give you that number. If it's a different chip, maybe it's some very high power audio amplifier that it may be, different. It just depends on whatever op amp you select. Yeah. Okay. Things you can do with an op amp. You can do all these things. I'm not going to go over all of them. I'll point out that I can skip that one. Okay, so we had so that's a better inverting amplifier. But if you wanted to have a non-inverting amplifier, so you wanted to put a signal into the positive one here, and you wanted to get a positive out and have a positive gain, here's your equivalent circuit here. Okay, do you see how we get the equivalent circuit from this thing? Okay, we know R is grounded. R is grounded here. You have 2 resistors going to V out, 2 resistors going to V out. And from one of the golden rules, we know that V in is going to be equal to this point here. So that is, you're going to have V in at this point here. And from the second golden rule, you know that all the current flows through here, through either resistor, because no current's going to flow into the op amp itself. That's the second golden rule. So you have one current. If you have a current and a resistance and V in, you have V equals IR. And then the difference in voltage between here, V out minus V in, that's the voltage drop across this resistor, is equal to the current times RF. So now you put these things together, do a little bit of algebra, and you come out with a gain formula, V out over V in, is instead of minus RF over R, you have RF over R plus 1. So it's a little more complicated if you want a non-inverting amplifier. And all that means is if you put a positive voltage here, you're going to get a positive voltage out there. Or if this increases, the output will increase. Okay, you should get used to looking at a circuit like this, drawing the equivalent circuit, and be able to come up with the formula for it. We're going to do that several times here. Skip this. Skip this one. Okay, now we get to the interesting part. You can do math with op amps. Okay. You can sum. You can take the difference And then you can do calculus, differentiate, integrate. I'm not suggesting you build a circuit that will actually do this to, calculate numbers for your homework, because it's analog. You still want to use digital for that. But anyway, it can do that, and there are uses for it. Okay, a summing amplifier here. You have voltages going into a number of resistors, and all of them go into the minus one feedback resistor. So here's equivalent circuit. And you go through the usual algebra so that if you assume all the resistors are equal, then you have one gain, RF over R, and then just whatever voltage you have here, it's just going to sum the voltages. So if the gain is minus 10, then it's just the minus 10 times the sum of these voltages. Okay. If you wanted just the sum of the voltages to be V out, then you'd make RF equal to R, have a gain of minus 1. Differential amplifier, I'll skip that one. Okay, now calculus, the last two parts of this, calculus. It takes a time derivative of the voltage you put in. Okay, so what could be simpler than this? You just replace the input resistor by a capacitor, and you're still going to put it into the minus, because you still want the negative feedback here. Okay, here's the equivalent circuit. Capacitor, resistor, current. Since this is grounded, this point is 0 volts. The current's the same through each one of these. Okay, remember that I said that the capacitor doesn't pass DC voltage? Correct. But if the voltage is changing, changing voltage can get through a capacitor. Because if you put charge on here, it's going to repel charge from here, so it looks like a current. Well, it effectively is a current. Okay, so we know capacitance is ratio of charge to voltage, or the way I remember it, the mnemonic is Q equals CV. If you double the voltage on a capacitor, you're going to double the charge. If you want to get a higher charge on a capacitor with a fixed voltage, you make the capacitance higher. So both of these things are linearly proportional to the charge. So the current is dq dt, right? And then you plug this in, and the current is equal to C times dV and dt. dV and dt across here. And then you get this. And finally, you get V out is equal to minus RC times the derivative V in dt. Ah, RC. Hey, we get the same tau. Isn't that interesting? That again, tau is equal to RC, which is dimensionless. Oh, sorry. It has the units of time. It has the units of time. Right? Because voltage, time in the denominator, we have to have time in the numerator to cancel out the units of time. So what I meant by dimensionless is, for a sine wave, the gain is just omega times tau. What could be simpler? Omega times tau. Questions on the differentiator?
Professor, is that a gain formula you put in the bottom right-hand corner for any sine wave, or just for the differentiator? If there's a sine wave across the differentiator?
Yeah, because yeah, yeah, any sine wave, right? Any sine wave is going to give you a gain of this, and it's frequency dependent, right? If you go to double the frequency, voltage is changing faster, twice as fast, so the derivative changes twice as fast. So that means the output is going to change. The output's going to be higher.
Sorry if I missed this, but this only works for alternating currents, right? So would it work
Right.
for like a would it work for like a sawtooth function or something similar to that? Or a square wave?
Very good question, because yes, you're going to do that. Yeah. I mean, yeah, this formula works in general here. The derivative, whatever voltage you're going to get out is going to be the derivative, time derivative of anything.
Yeah, as long as it's some form of alternating current, I'm guessing.
Well, it has to change with time. That's the only criteria here. Yeah.
Mm-hmm.
Yeah. I mean, it's when you take the derivative of the sine wave, you have, sine omega t. So when you take the derivative, an omega is going to come out of taking the derivative of sine omega t. So that's how you get omega here. It's very, very simple to show omega t from this. Any other questions before we move on to the integrator? Okay, let's take a guess. Let's take a guess. So, if in the this is a formula, tau dv dt. What do you think the formula would look like for an integrator? If you just wrote v out equals to something times the integral of v in dt. Any guesses?
Is it going to be a tau from an RL circuit?
No, there's still a capacity. Yeah, okay. I forgot to tell you that the integrator is just going to reverse we're just reversing the R and the C. We're not putting in an inductor.
Is it 1 over tau, the integral of v dt?
Yeah, good question. Sometimes physics is so simple. Okay, time integral of a voltage. The integral of dv and dt. We've just switched the two components here. Okay, and we get an equivalent circuit like this. We go through a little bit of, tiny bit of mathematics, mumbo jumbo, even a little bit of calculus. But now, to write current is dq dt again, and then put in the capacitor. And then we want to integrate the whole thing to get rid of this derivative here. So here's what we come out with. The negative again, because we're putting something into the negative input of the op amp, 1 over tau, integral dv and dt. So here's voltage, time here, so we have to divide by time to get the dimensions to work out. For a sine wave, you could probably guess this, right? When you have an integrator, you have 1 over omega t instead of omega t. Yeah, so this formula works for any voltage that's changing with time. Okay? Doesn't have to be a sine wave. Questions on this circuit? I think this is the end of the new material. Then we're going to go over the experiment. Okay. Oh well, here's a homework. Oh, a homework example. Yeah, yeah. Okay. These are fun. These homework problems are fun. Okay. Two things. Given a circuit, write the equation, or given an equation, draw the circuit. Okay, so here's a circuit. Look at this R. Okay, X is a voltage, and Y is a voltage, and V out is a voltage. Okay, so you can see that if you apply a voltage here on X, the gain of these two resistors is going to be minus 5R over R, or minus 5. So from X, you're going to get a voltage out here that's minus 5X. Okay. If you go over here, we know this is an integrating circuit, far left. So voltage Y, you're going to get a voltage out here that is, sorry. You're going to get a voltage out here that's the integral of 1 over RC times V Y dt. Integral of, sorry, Y dt. So that's a formula for the voltage here. And then you're going to take this voltage. This is an input voltage now, and that's going through unity gain of minus 1, 5R over 5R, which is minus 1. So then that gives the voltage Y giving a voltage out is going to be plus 1 over R times Y dt. Okay, so the X and the Y voltages are going to give you an output that looks like this. Okay. It's often good to start with something that's simple. I mean, you could start over here. Questions? Yes, let's move on to the other type of problem. You're given an equation like this. Here's 3 terms. V out equals plus 4x minus 6y minus 3 dz dt. This is a little bit harder than the previous problem because you can do it with a different number of op amps. It's not always going to be 2 or 3 op amps. You could do it with 4, say. Okay. Okay, so let's begin with the Y voltage since we already have a negative sign here and it's just, you know, no derivative or integral, minus 6. So you want a gain of minus 6. So you want to pick feedback resistor 6 times the input resistor. Okay, so we draw that. Okay. Then we want to take, well, what do we do next? We want to take this one or this one. Okay, I'll do both of these. Okay, this is a negative sign already, so that's kind of nice. Okay, so when you have a positive sign, you may need 2 op amps because each op amp is going to give you a negative sign and that'll give you a positive. So it's good to start with a negative one. Okay, so here I put a capacitor and a resistor, and we know that's an integrator. differentiator. And so it's going to be minus RC times Vn dt. And then you know that tau is equal to 6 RC, right? And you want that tau to be equal to 3. So that's tau is equal to 3. So that means 6 RC is going to be equal to 3. So that's how you get C is 1 over 2R. So that would give you the value for C to give you this number 3 here. Okay, finally, when you have a positive here, you know, unless you want to put some input on the positive one, which, yeah, let's not do that. We're going to need a second op amp because each one's going to give you negative. Okay, so we're going to have one here, X, and 4R over R is going to give you a voltage out here that's X times minus 4R over R, or 4, minus 4X. So here you're going to get a voltage that's minus 4X. And then it's plus 4, so you just need a gain of minus 1. So from minus 4X, 6R here and 6R here gives you a gain of minus 1. So you have a minus and a minus, so then you're going to get out a 4 plus 4X, plus 4X. Okay, so you're gonna do these some of these for your homework. I think they're fun. Any questions?
So the actual value of R doesn't really matter. Just the ratios between the R's matters, right?
Yes, right. I mean, yeah.
So you get the same. So you'll get the same behavior if you have, like, assuming nothing breaks, you'll get the same behavior if you have like R be like 10 ohms as it would be like 30,000 ohms.
Yeah. In general, for op amps, especially like the 741, you don't want to have too lower resistors, too small resistors, or too high of resistors. Like, you don't want to have, you know, R is 1 ohm, 6R is 6 ohms. You know,
yeah, you don't want to fry anything.
Or even meg ohms, you know, 1 meg ohm, 6 meg ohms. You know, pick something reasonable. Yeah. Good question. Okay, that's for the homework. I'll put that on right after the lecture. Okay, for the experiment, don't forget to power the chip. And don't forget to turn the power on. Okay. We're here to help. Ask lots of questions in the lab. Come to Zoom on Monday. Email questions to the TA or to me. Okay. I guess you've had a little experience with the breadboards, right? The proto boards. These 5 pins are connected underneath, but they're not connected to these 5 pins that are connected. Okay, and the vertical pins are connected. And you're going to put your chips in something in, like, across this this valley here. So then you can connect, you know, like this pin here to the green wire. And that's what your 741 looks like. Okay, so the last thing is the lab report. They're going to be written from the last 4 now. Okay. And here's a template. Stop sharing that. Screen. Hold on. Here it is. Okay. Let me get out of here. Stop sharing that one. Template. Description. Okay. Okay, here we go. Darn it. Here we go. Okay, can you see this?
Yeah, we can.
Great, okay. So here's a template. You can use this or you can use LaTeX, whatever. This is a little bit older version, but anyway. Okay, you need the title of your experiment. We're not having lab partners. You have to have the date, your name, a maximum of 4 pages. Okay, I don't want you to go wild with descriptions. Minimum's 11-point font, 1 inch margins only. I want you to write an abstract. And an abstract is a short summary of, I would say, 4 to 5 sentences even, not 8 sentences. And in the abstract is your elevator speech, specifically what you did. Maybe not why you did it, but what did you do? I measured blah, 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 blah. Number 2, what you found. I found that this happened when I did this, and this happened when I did this, and I got a value of this for this. And that was a little bit smaller than what I expected because the blah, blah. Okay, keep it simple. 1 short paragraph, specifically what you did, what you found. This is practice. This is practice in figuring out what is important to people and what is not. If you want to catch people, you want to catch people's interest. People will read the title of something. Hey, that sounds interesting. Then they want to see maybe a synopsis or an abstract like this. Oh, that sounds interesting. And then they'll go a little further. Keep it simple. So some publications have motivation in them, but we don't want to do that here. I don't want motivation in this. Okay. Keep an eye on organization. Introduction should only be 1 paragraph. List of equipment. Procedures and results. Briefly describe the procedures. You have to include all the equations. And describe what you found. Often the plots, the figures are what you found. Here, are the result. You have to have circuit diagrams. Every figure has to have a caption to it. Okay, not a title, but just a caption. And figures should be fairly small, and you can save space by wrapping text around the figures. Figure out how to do that if you haven't done that. Very important, make sure that you can read all the numbers. and the lettering in the figure. Excel is so bad at giving you very small fonts on some of the numbers, and if you can't read it, you know, the TAs are going to take points off. They're too small. Remember, connect points unless you have a theory, and then put the theory that fits the data. Summary is just a slight expansion of the abstract. Here's what I did, here's what I found. And tables are very good for summaries. Here's the item, digital multimeter. The measurement was this. I expected this. The battery internal resistance was this, and I expected this. Okay. Keep it simple. You want to keep under the 4 pages. Anyway, so read through this. You can use this template if you want, or use your own template. Okay, any questions on this? We used to have reports on every experiment, and I shortened it to only 4 experiments. Yeah, we have to get used to writing reports. You know, we're going to be writing reports for our bosses, for publications, for grants, for scholarships, you know, all sorts of things. So we want to have practice with it. We want to have practice with the abstract, with the elevator speech. Simply, here's what I did, here's what I found. Okay, you'll be able to find this in the from the calendar page. Okay. Okay, please read instructions before coming to the lab. Visit the Monday discussion section. We can talk about things. I'm here to help. Okay. So I'm sorry to keep you so long again. Wow, almost 5 minutes before the end. Any last questions? Okay, good luck on Thursday and Friday.
Thank you. Thank you.
Okay,
Thank you, Professor.
Thank you.
Thank you.
take care.
Thanks.